Good afternoon and welcome to Kennedy Space Center for our second news briefing on the GOES mission. I'm Steve Cole from NASA Communications. We're getting ready for the launch Thursday of the next U.S. weather satellite, NOAA's Geostationary Operational Environmental Satellite S. Today we're going to give you a preview of how GOES-S will advance scientific discovery and weather forecasting and help save lives from natural hazards like wildfires and severe storms. We have 5 panelists for you today. Let me introduce you to them. Our first panelist will be Dr. Dan Lindsay, GOES-R Senior Scientific Advisor at NOAA. Dr. Louis Uccellini, Director of NOAA's National Weather Service. Dr. Jim Roberts, scientist at NOAA's Earth System Research Laboratory in the Office of Atmospheric Research. Dr. Kristen Calhoun, research scientist at NOAA's National Severe Storms Laboratory. And George Morrow, Deputy Director at NASA's Goddard Space Flight Center. We'll begin with remarks from our presenters, and then we'll take questions from the media here at Kennedy. If you're watching on NASA TV, you can ask questions too via social media by using the hashtag AskGOES. Okay, we'll start with our first speaker. Dan?
Thanks, Steve. On Thursday at 5:02 Eastern Time, NOAA, in collaboration with NASA and United Launch Alliance, will launch GOES-S into space. Upon reaching geostationary orbit about 3 weeks later, it will be renamed to GOES-17. It'll spend about 6 months at its longitude of 89.5 degrees west, and then it'll be moved over to 137 west, which is over the eastern Pacific Ocean, and at that time it will become the operational GOES-West satellite. GOES-17 has the same instrumentation as GOES-16, which has been providing us amazing imagery for about a year now. But it will have different coverage. Since it's centered over the eastern Pacific, it'll actually see from really the central continental U.S. across the eastern Pacific, including Alaska and Hawaii, and all the way out to New Zealand. So combined with GOES-East and GOES-West together, we can see from the coast of Africa all the way to New Zealand. What I'd like to show today is share with you some highlights from GOES-16 over the last year and tell you some things that we can look forward to with GOES-17. If you could go ahead and show the first animation, please. So this first example is one application that we've seen from GOES-16 from the Advanced Baseline Imager, and this is looking at severe storms. This is centered over Central Texas from 28 March of 2017, and the entire animation that you're looking at that's repeating is 20 minutes long, and each time step is 30 seconds. And this is representing one of the unique capabilities that we have with GOES-16 and we'll have with GOES-17. What this allows us to see is features of thunderstorms that are changing very rapidly with time, something that we were not able to do with the previous satellites. If you look carefully, you can see bubbling cloud tops. That's a sign of very active convection. And if you have a really sharp eye and you look at the side of the cloud of the storm there in the center, it appears that we can actually see it rotating. This is something that we didn't have any chance of able to see with the previous satellite. So in concert with Doppler radar, weather forecasters can use this type of technology in order to get a little bit more information about severe storms. One thing that that example also highlights is the ability to use mesoscale sectors. And what that means is, what we can do is we can take a 1,000 by 1,000 kilometer area and move it to an area of interest. One example would be over a hurricane or perhaps over the central U.S. if we're expecting severe storms. And if we zoom in, we get that 1-minute imagery over that area. And that's something we did not have before. GOES-East has 2 of those sectors at all times, and GOES-West, once it becomes operational, will also have 2. So that'll give us 4 of these sectors that we can position over the weather events of interest. Could you go ahead and pull up the second animation? The next example I wanted to show is an example from a different instrument. This is something brand new. It's called the Geostationary Lightning Mapper, or the GLM. This is the first time we've been able to detect lightning from geostationary orbit from space. The example here shows the active time in the tropics from back in late August going into September. At the very beginning of the loop there, Hurricane Harvey had made landfall, and if you look carefully, you'll see Hurricane Irma coming in from the east here in just a minute. What's plotted here, the flashes are the actual data from the GLM, and it represents lightning flashes that we can see from space. Here comes Hurricane Irma. You can see it approaching the northern Leeward Islands. There it goes, skirting along the northern part of Hispaniola, passing north of Cuba, and eventually making landfall in Florida. And there's Hurricane Jose coming into the east. One thing you may notice is much of the lightning is actually occurring away from the centers of circulation. It's occurring in the outer rain bands, and these are in the most convectively active regions of the storm. The final example I want to share with you is actually for detecting wildfires. If you could go ahead and cue the third example, please. Third animation. This is an example from 3 September 2017. You may remember they had a very dry summer and into the fall up in Montana. This is western Montana. And what we're looking at is a combination of a couple of different satellite products from the ABI. One is able to detect the hot spots from the fires. Those are the red and yellow areas that you're seeing. We're not seeing the actual flames, but we color code the hot spots based on how hot the pixels actually are. And then we can also see the smoke. You can see the smoke forming and then moving off downstream. This is a really nice tool for forecasters in order to be able to, first of all, inform emergency managers where the hot spots are located so that they can get the fire crews out really quickly. And it also allows them to track the smoke so that they can provide that information to the Weather Service and to emergency managers who are worried about things like visibility issues or other bad things that smoke can cause. That's all I had for now, and I'd like now to pass it on to Dr. Uccellini.
Excellent. So before I show several of examples that I also have, I just wanted to note, I've been reflecting on Vern Sumi, who is the father of weather satellites. He was in his prime when I was a student at the University of Wisconsin in the late 1960s through the 1970s. He had an idea a minute and was the first to envision the power of placing satellites in geostationary orbit. He often said to people who were trying to see the vision he saw, "The Earth stands still, the clouds move." I've been sitting here thinking maybe he was the only one who could have imagined then what the new GOES provides to the forecasting community today. So let me start by emphasizing that every forecast, whether it's 1 day, 2 days, 3 days, out to 7 days in advance, depends on sophisticated numerical models, the world's fastest computers, and a global observing system. And NOAA's satellite data provides the backbone for the global observing system and is the critical element for weather forecasting in the extended ranges. The geostationary satellite, the GOES series, is a crucial component of today's global observing system. This week we are launching GOES-S, our latest and greatest geostationary satellite. GOES-S will complete our high-resolution satellite coverage of the entire country, delivering better observations faster than ever before. I'm sure you've heard this many times. The satellite will scan the skies 5 times faster than the current GOES-West satellite, 4 times the spatial resolution, 3 times spectral bands, and with of how amazing that all looks when it comes together. Now, before the launch of GOES-16, the National Weather Service, various representatives emphasized how excited we were about the new GOES series. Our experience with the GOES-16 data has gone beyond excitement. We have watched in amazement what GOES brings to our forecasters every day. We've already seen the results of this advanced technology in GOES-16, and it has exceeded our expectations. So we can cue the first video, please. So this is a video of Harvey approaching Texas, making landfall, and you see that incredible deepening as it came on shore. That deepening, that was an increase from a Category 2 to a Category 4, was captured beautifully on this image. And it not only captured when the eye wall would approach the coast, but also when the back of the system would be affecting Texas. Now, why is this important? Because this is the period of time that the local forecasters in Corpus Christi were in communication with the first responders and the emergency managers. And here you have another view of that storm. You can actually see the clouds sinking into the eye. This is the first time we've ever seen that. Really phenomenal. I believe this is the 30-second imagery. And as that eye approached the coast, We could time it almost exactly. The first responders went out and rescued over 200 people who were stranded on those islands and along the coast of Texas. And then, of course, we informed them as the back of the eye wall was coming at them, and they would have to get back into their hunkering position. So this was an example that we were seeing in real time, and I can attest to the fact that many of us were just staring at that imagery, gaping at it, watching what the increased temporal resolution was actually showing us in terms of the eye wall dynamics and the deepening of that system. If we could go to the next video. We've heard about the wildfires situation in the United States. This is an example that occurred on March 6th, 4 days after we started getting the imagery in the engineering checkout phase. And you can see those fires developing, and of course the brighter is the hotter. Look at in northern Texas where that fire is developing, and then it surges southward. Okay? That's what can kill the firefighters who aren't prepared for that kind of behavior. These fires were being reported by our forecast office to the local officials. The observations we had and our phone call to them was the first indication they had fires in their area. So what has happened since then? I mean, after that event, we were getting all kinds of testimonials, not only from our forecasters, but from the first responders, that we saved lives 4 days after getting access to the data in the engineering checkout phase, well before we even went operational. Last weekend, we had a tabletop exercise organized by those first responders in Kansas, western Oklahoma, northern Texas, in Amarillo, Texas, with our forecasters, with our observing system setting the stage for that tabletop exercise. They already know they've come to rely on this data for the way we will operate with them and provide the impact-based assistance support services to them. So we were very early, before we even accepted the satellite in an operational mode. We were seeing this data while the whole satellite, the dissemination system, was in engineering checkout phase, and this was really the first time in the history of the GEO series that we were able to do that. And 4 days after getting access to it, with a trained workforce, we were able to work with local emergency managers to save lives. So this didn't happen by chance. I've already alluded to the fact that we had access to the data. The GOES project actually worked the communication lines, ensured that we could receive the data. The receive stations were set up in the Western Pacific first so that we could practice with the Himawari data, which was already flowing at that time. And we trained our forecasters with that, through that project resource as well. So we were ready 4 days after we received the data. So the last example I want to show now is after operations, one of the blizzards along the East Coast. This is the January 4th case. And the thing that's remarkable about this case, you can see the vortex spinning up very rapidly, about 800 miles off the coast. But the snow, the heavy snow along the coast, was occurring in that area that was developing and flowing into a jet system over New York. And all the heavy snow that we were experiencing was about 800 to 1,000 miles away from the center. So I've said in a number of examples that I've seen in real time that this data set's redefining mesoscale meteorology. It's also redefining synoptic scale meteorology. We think we understand the structure of these big cyclones that produce those kind of events along coastal regions, but we're seeing that they have unique characteristics as they form, and this satellite system really does a great job in picking that up. So in closing, the National Weather Service is ready and eager to infuse the GOES-S data in the forecast process, just like we infused the GOES-East data, to enable us to monitor the storms every 5 minutes, every 1 minute, and in these special areas every 30 seconds, just as we're able to do with GOES-East. And we expect to be doing that even as we go into the engineering checkout phase. GOES-S will provide more accurate data with higher temporal resolution to track storm system, lightning, wildfires, the coastal fog, volcanic ash plumes that impact the western U.S., Alaska, Hawaii, and the central to eastern Pacific Ocean. There are unique aspects of these intense Pacific storms that we'll be able to observe more accurately and use in our forecast process. I believe very strongly GOES-S will improve the services and scientific understanding for the western U.S., just like GOES-East has for the eastern U.S., and is another step forward in our overall effort to build a weather-ready nation. So I thank you, and Jim?
Yeah. Thanks, Louis. I wanted to, as part of the NOAA FireX project, I wanted to explain how GOES-S and GOES-R satellites in general are going to help us understand and manage the growing wildfire problem in the western U.S. I'm part of the steering committee for the NOAA FireX project, which stands for Fire Influence on Regional and Global Environments Experiment. It's a 5-year project. We're right in the middle of that, and GOES is coming along just in the nick of time as far as our intensive experiments are concerned. You bring up the first image. Basically, you'll see what the scope of the problem is. This is a 10-year projection of the areas where we're going to have fires of concern in the western U.S. And you can see it's pretty much the whole western part of the country. We'll need to understand the scale of the problem because we're in an era where we're going to have increasing wildfire because of a number of reasons. There's a warmer and drier climate, especially in the U.S. We've had past policies of fire suppression that we're going to have to move away from. And one of the reasons we have to move away from that is because the forest ecosystems in some respects require fire for maintaining their health. So that's kind of given us a growing recognition that we're going to have to learn to live with wildfire. And if we can see the next slide, we actually have a national strategy that's captured that. And basically what it says in a nutshell is we're going to need to fight fire where needed, and we're going to need to allow fire where we can. There's a number of things that go into that as people were concerned about the impacts of the atmosphere. We need to understand what that means for the atmosphere on timescales from the local and immediate to the long-term and continental scale. And some of those considerations have to do with accurately predicting where the smoke will go, knowing what the composition of the smoke is and how that's going to evolve so that we can predict health impacts and provide the data for the people who need to make those decisions about fighting fires on an immediate basis. The next slide shows part of the products that we're developing now that are the next generation products for understanding fire. And this slide is actually part of our high resolution rapid refresh system, which is based on MORPH chemistry and physics. Right now it has an inert smoke tracer in it. And the smoke tracer is based on fire detections from the MODIS instruments, which are on polar orbiting satellites and give us once a day coverage. You might remember the Thomas fires in Southern California a couple of months ago. We missed the first day of that fire with this system because it happened after the MODIS overpass. That, as you've seen from the videos, will not be a problem with the GOES system. It will be looking down 24/7, and we'll get imagery almost immediately. I want to show you, this plot is actually from the day after the one Dan showed. It's actually for Labor Day 2017. I want to show you the GOES video from that day. If you could bring up the video now. You can see, especially if we were to look at it in detail, that the correspondence between the model and this video is remarkable. And what it does is it lets us make predictions. For example, I was at the reservoir on the Front Range of Colorado when the smoke came in. You couldn't even see the mountains. And the wind picked up. I thought, oh, great, it's going to clear up. But as you can see from the video, the wind picked up and it got smokier. So that's the kind of thing, just to kind of bring it home, that we'll be able to actually see almost real time with these satellites. What we're going to get from the GOES information is we're going to get plume forecasts, as we've seen. We're going to get fire temperature, which is very important for us chemists. We really need to know fire temperature to really accurately predict what the chemistry will do. We'll get aerosol optical depth, which will give us a sense of where the particles are going. And particles are one of the most immediate health problems that happen in fires. So that will really help people who are concerned about health effects. And in addition, we'll probably be able to get plume height because we'll have 2 satellites, and stereoscopic image can potentially get plume height. That's also very important for us chemists because some of the plume chemistry changes with plume height, and the transport footprint of the smoke also changes a great deal. And the other thing that's going to benefit us is we'll be able to get the state of Alaska, which we were not able to do with the other GOES satellite. Now, eventually, we'll be able to put full chemistry into the high-resolution rapid refresh model. And in order to do that, we're going to have some intensive experiments that are shown on the next slide happening in the fire season of 2018 and 19. Let me bring up the next image. That's kind of just summarized here. We're going to use all these resources, GOES satellites being chief among them, to study chemistry in situ and relate that to some of these products that I just talked about. And what we want to do is we want to fine-tune our capabilities so that we can use the remote sensing on a routine basis to understand what the likely composition is of the smoke, where it's being transported. And this is going to give us faster and more complete information that we can provide to the first responders. We can also provide it to the people who need to make health impact statements, need to notify people who might be at risk, and that kind of thing. And this way, we're hoping to minimize the impacts of wildfires as we learn to live with fire going forward. Now we want to hand it over to Kristen.
All right, thanks, Jim. Those of us in the severe weather community are really excited about the data we're seeing from GOES 16. I mean, you can already tell in the visualizations we've seen why we're excited. And we're also eagerly anticipating the increased coverage from GOES S across the United States. For the first time ever, space-based observations from geostationary satellites and ground-based observations such as Doppler weather radars are in cadence with each other, providing the ability to create a top-to-bottom linked profile of a severe thunderstorm through direct observation. This has a direct impact on severe thunderstorm research, diagnosis, and hazardous weather forecasting. With the Geostationary Lightning Mapper, or GLM for short, and if you could show the first video here. Lightning data can tell us a lot about storm updraft strength and how quickly a storm is intensifying. We can see how large and widespread the lightning flashes are, providing information relative to lightning safety and storm strength. Forecasters can integrate this with their other observations to make a warning decision earlier and also with more confidence. And we've tested this now in the hazardous weather testbed, the NOAA hazardous weather testbed in Norman, and it's been really interesting to see forecasters integrate the lightning data into what they're used to doing for making that severe weather diagnosis. And they are making those decisions earlier and with more confidence now with this data. This additionally has a huge potential impact in the Intermountain West following the launch of GOES S. There will now be coverage for regions where terrain had resulted in blockages of the ground systems. Where there were previously gaps in coverage, forecasters will now have the opportunity to fully understand and diagnose storms. This will impact forecasts and warnings for flash flooding in areas like slot canyons and can help predict with the onset of lightning in the national parks and recreation areas. We are already investigating applications with the new data available from GOES 16. And if you could show the first still image. So this is Hurricane Harvey. On the left, we have the ABI, and on the right, we have a density plot of GLM, essentially. So the base events and then flashes are noted. So we had an active tropical season, obviously, in 2017. And we're now beginning to really research ideas and reasons why lightning activity in the eye wall and outer bands are different and can help either predict trends in tropical cyclone growth or tell us unique things about regions of landfalling systems. With Hurricane Harvey, as seen here, we noted a lack of lightning in the eye wall at the time of landfall, but we saw increases in the outer bands with the cells over the Houston area, signaling the strength and longevity of these individual storm cells as they came in and across the area. With Maria, now if you could show the video. So this is following on to what Dan showed earlier that ended with Jose. Now we have Maria coming in on the southeast quadrant of that image. We saw increases in the lightning eye wall during the period of intensification, and then also following landfall with Puerto Rico. It was after this that we saw a lot of increases in the outer bands. So we are just beginning to tie these observations with ground-based systems to highlight specific areas with higher likelihood of severe weather, with the goal of helping forecasters predict and increase lead time for things like tornadoes during landfall. Additionally, the near continuous information provided by these systems have already impacted our research and understanding. For instance, as Dan showed earlier, we have seen evidence of rotation of the mesocyclone from supercell storms from the GOES-16 ABI and are examining ways to integrate this data as well as data from new instruments like the GLM into our high-resolution convective models. Simultaneously, we're also exploring AI and machine learning methods to better synthesize this data with ground-based observations with the ultimate goal of better predicting the likelihood of onset of dangerous severe weather, such as large hail, cloud-to-ground lightning, and tornadoes. The temporal and spatial resolution of both satellites combined will give us the ability to test and better utilize them simultaneously. So like, for instance, across the Central Plains, we'll have both satellites looking down. So following the launch of GOES-S, we are excited to begin exploring what additional information the stereo overlap and multiple viewing angles will give us in relationship to severe weather. As Louis noted earlier, we're already seeing the impact of the temporal and spatial resolution from GOES-16 in severe weather research and forecasting. And we're excited to continue to explore the impact of these tools to provide a better and more timely information to the public when severe weather threatens. Thanks. And now, George.
Thank you. So Goddard Space Flight Center is proud of the role we have played for more than 45 years to support NOAA's work in providing the most accurate weather forecast possible. Goddard pioneered Earth observation from geosynchronous orbit, beginning with the Applications Technology Satellite 1 in 1966. Please show my first image. In all, 6 ATS satellites were funded by NASA and launched by Goddard between 1966 and 1974, including ATS-3, which provided the first color image of the Earth. The ATS series was followed by the synchronous meteorological satellites 1 and 2 that provided the advancement necessary to justify the beginning of the NOAA-NASA partnership on GOES beginning in 1975. Since then, Goddard has managed the development and launch of every GOES satellite for NOAA. NASA Goddard's primary role in the modern GOES program is to use our expertise and experience in designing, building, launching, and operating satellites in order to deliver a spacecraft that meets NOAA's exacting operational needs. But we may also play a critical role on the science side, both in the long-term development of the instruments on board and also in the creation of GOES data products and the ultimate use of those products for fundamental research into how our home planet works. Let's start with NASA Goddard's role as the R&D arm of the partnership. When GOES-S becomes GOES-West, it's fair to say that the entire country, or at least anyone who looks at a weather forecast, is depending upon the instruments to work immediately and consistently, essentially with the flip of a switch, as you heard earlier. But as I described, there are decades of development behind those instruments and the data products that are derived from them. When NASA Goddard launches the Earth observing satellites, we're typically demonstrating new technologies. A great example of this demonstration to operations chain of events is the geostationary lightning mapper that you just heard about. At Goddard, we flew the lightning imaging sensor on our tropical rainfall measuring mission launched in 1997. You can draw a line from that successful technology demonstration to the GLM on the GOES-R series, the first operational lightning mapper. Please show my first video. In addition to the weather monitoring, SUVI instrument on GOES-S is a direct descendant from NASA's Solar Dynamics Observatory instruments. Solar Dynamics Observatory is in orbit, monitoring the sun from geosynchronous orbit with continuous downlink. In addition to needing the instruments to work right away when GOES-S becomes GOES-West, data users also need to know how to handle the data right away. In order to enable that, teams at NASA, NOAA, and universities use NASA data in what's called a proving ground. Scientists use data from MODIS instruments on the NASA Terra and Aqua satellites, for example, as a proxy for the Advanced Baseline Imager on GOES-R and GOES-S. This proving ground helped develop data products for cloud cover, atmospheric moisture, dust plumes, and different nighttime cloud layers before GOES-East and now GOES-S ever reach orbit. Finally, NASA Goddard scientists like to get their hands on every available data stream possible. Please show my last video. The GOES-R series is making groundbreaking observations with higher spatial resolution, temporal resolution, and in more wavelengths. For researchers, this quite simply means we are observing weather events in more detail than ever before. We have data that we did not have before. The freely available data from GOES-S of clouds, the thermal properties of storms, lightning, sea surface temperatures, the list goes on, will provide a crucial view as NASA scientists continue to research to understand Earth as an interconnected system. And to bring it back to the beginning, new understanding of how our home planet works will ultimately find its way to better forecasts in our daily lives. And now, back to you, Steve.
Okay, thank you, and thank you to all our panelists and for sharing all those really amazing views from space. Now we'll take questions from the media here, and if you're watching on NASA TV, you can ask a question too via Twitter by just using the hashtag AskGoes right there on the screen. We'll start here with reporters at NASA Kennedy. If you have a question, please raise your hand. We'll get a microphone to you. And please state your name and affiliation. We'll start right here in the front row.
Hi, Ken Kramer, Rocket STEM and Space Up Close. For Louis, I think. I wanted you to go a little bit more detail about how you were able to get this life-saving information out in Texas so quickly. You said 4 days. I mean, were they ready and then Harvey just happened? How did that all come about? Thanks.
So this is my thanks to the GOES project because early on they looked at this as not just putting a new satellite up into space with incredibly new imagery capabilities. There was a recognition that we had to be able to move that data around fast to keep the latency time down. That we had to get that data to the fingertips of the forecasters, so it had to come on to the AWIP system, and the forecasters had to be trained. And that's exactly what the project funded. It's what we did working with them from the Weather Service perspective. And so on March 2nd, when through the engineering checkout phase, they were ready to release that data in real time, still within that checkout phase. It wasn't just a matter of it coming to a few scientists like we used to do. I worked for NASA for 11 years, and we used to see data in the engineering checkout phase, but nobody else did. Well, that data started flowing right through the big pipes that were supported, right to the AWIP system, to trained forecasters, and they knew what they were looking for and looking at. They were excited. I got a lot of positive emails that day on March 2nd. And then by March 5th, 6th, this fire situation, which was already showing signs of starting up in that area of the country, but really took off. They knew what to do with it, and of course they have all the connections with the local first responders and emergency managers. So that part of it, worked as we expected. What was really amazing was how fast they were able to use that data and to make it work for them. And the testimonials coming from the first responders confirmed. I was getting letters and emails for weeks after that, and I think the tabletop exercises that are being held today with this data set as a focal point for initiating the tabletop exercises is another testimony to the importance of it already. So that's how it works, and it was, it was working for Harvey. It was working during the whole hurricane season that way, and as we went into the winter, we of course operationalized the data. We're now in an official operational mode, and we were we were moving forward very rapidly even through that phase as we approached the winter and the complexity of the winter storms. So it's really amazing, and when you see all this imagery, you see the details and the different applications. It's a really remarkable story, actually.
Okay, we'll take our next question from social media.
Will the data collected by GOES be available to the general public?
We have arrangements made with the various partners that we have that release this data through the media, and they have downlinks as well. There's a way of remotely downlinking this data set, so if they can do it for GOES East, they'll be able to do it for GOES West.
My name is I'm the chief scientist for the MyRadar mobile application. It's sort of a follow-up question to this one. It was mentioned that there were interest in using artificial intelligence for synthesis of the GOES data, and those types of efforts are more productive if you have like longer time series, and the more data you have, the better that sort of effort is. So in the context of the sort of practical constraints of what that could look like, are there plans for access and availability for long time series of GOES data, perhaps as part of the NOAA Big Data Project?
I'll take that. Yeah, so at NSSL, at the National Severe Storms Laboratory, we have a couple of AI projects already underway. What we've done till now, because we do need a long time period of data, is work with the data we already have on the ground, mostly the ground-based systems like the weather radar and some of the cloud-to-ground lightning data from the National Lightning Detection Network. One of the things that I think will make it really better, though, is if I can retrain these systems. So I have one that we developed to predict. It was a probabilistic cloud-to-ground lightning. So any individual storm, we look at the next 60 minutes, the likelihood. And then we're blending environmental data from models and also information from the radars and stuff like that. I look forward to making it better by taking GOES-R and GOES-S, 16, 17. But I'm going to need about a year. What we did is we trained it across a year. We grabbed a bunch of days individually that should not be synoptically kind of tied to other days. So we said we're going to grab the 3rd, the 7th, and the 21st of every day, and that's going to become our training data set. So yeah, I need about a year before we can really start utilizing AI with this data, but I think it'll have quite an impact on what we want to do with it. So, and yes, so part of this, I have a funding grant through the NSSL to archive data, and we're doing an open access server at the University of Oklahoma in coordination with that. And one of the things we're bringing in are some of the level 2 and higher level algorithm products, and we're looking forward to including those kind of things in our AI. But yeah, the idea is it's to make it accessible to the academic community and stuff for these kind of like joint severe weather research projects.
Okay, thank you. Do we have any other media questions here at Kennedy? Okay, if not, then that will conclude. Oh, one last minute one from Ken here. Ken Kramer.
Nobody else has a question. Let me ask. Talk a little bit more about this mesoscale data. You have 2 on each one, and how do you decide where to point it?
Yeah, that's a great question. That's correct. There's 2 mesoscale 1,000 by 1,000 kilometer approximately boxes that are available from each satellite, and currently GOES East has those 2. The National Weather Service has the ability to request the mesoscale boxes be moved to a particular area. So for example, say we had Hurricane Irma making landfall in Florida, and at the same time we had severe thunderstorms in North Dakota. And the Weather Service would make those 2 requests. They would take one of the mesoscale boxes and move it over Hurricane Irma. They would take the other one, move it over North Dakota, and that way you get 1-minute images over both of those areas. Now, in the event where there's 3 or more requests, a priority list has been established, where such that things like high risk of severe thunderstorms would rank very highly. Landfalling tropical cyclones or hurricanes would rank fairly highly too. And so in that situation, you have to go down and prioritize. Now remember though, with GOES West, we get 2 more. And so we'll have 4 at that point. Of course, the GOES West ones will be better for the western part of the U.S., things like fires in California or really any weather event. So it's a really nice capability, and the forecasters have utilized it quite a bit, both during the checkout phase and during the operational phase. One other thing I'll mention is if there's only one request at any given time, they can actually take the two mesoscale sectors, stack them on top of each other, and that's how we get the 30-second data. The thunderstorm example I showed and the Hurricane Harvey example were both from 30-second data.
Can I add something to that? So back in the day, when I was the National Center for Environmental Prediction Director, the big conflict in the hurricane season in the West really was the hurricanes approaching the East Coast at the same time that these fires are breaking out in the West. And we would have to make a decision in terms of these special observation days of which one do you choose when, and the hurricane generally won. What we're seeing over the last 10 years, and we've seen a lot of examples here today, is that the fire weather season out in the western third of the country is really becoming ferocious. And those kinds of decisions wouldn't be easy today. They're never easy, but when you have the hurricanes approaching the East Coast, it seems to, you know, what happens if you have a fire like the Thomas Fire going on at the same time that you have the hurricane coming in, right? So having the two-ball system is really going to be incredibly helpful in that regard in bringing those kinds of mesoscale views. And when that happens, we see things that on the mesoscale circulation systems, the gravity waves, the multiple gravity waves interacting with each other. I keep on, you know, pointing out to the research community, this is redefining mesoscale meteorology, and I think the applications part of that's going to be right behind it because we're going to be able to do the kinds of observations we need. And the other thing that's happening now is this overlap area over, I would say, the central third of the country. I think it's going to be good enough to do the kinds of experiments that Steve Holtz talked about earlier in the stereo world. NASA Goddard actually pioneered stereo imagery back in the 70s and 80s. We'll be able to get a lot of this data in real time now, so I suspect that you're going to start seeing applications in that world as well. So I think we're really looking forward to some exciting times here.
Okay, I guess we have one last question from social media. Joe? Oh,
The highest frequency that we can scan is every 30 seconds, and that's the situation where we stack the two images, the two sectors on top of each other.
Thanks. Okay, over to social media. One last question.
We seem to be in a golden age of weather satellites with GOES-R, JPSS-1, and soon GOES-S. Is the combination of data and imagery from these systems having an exponential impact on forecasting accuracy more so than any single weather satellite?
So you actually point to a very important aspect of the combination of the polar orbiting satellites with the geosatellite imagery. So the polar orbiting satellites have the sounders. With any kind of dwell rate, they're going to get a better signal to noise. So we're seeing now in the research community especially, and now even over to the operational community through NSSL, this calibration of what we're seeing in geo through the co-location and collaborative use of the low Earth orbiting satellites. So this will not only improve the radiances that we're ingesting into our models, it should also improve our height specifications for atmospheric motion vectors that we get from the geostationary satellites as well. And the combination of the wind and the temperature moisture measurements will, I believe, add more consistency and more accuracy to the model runs.
Okay, thank you all, and that concludes our briefing. We hope everyone will come back for the main event on Thursday when we launch GOES-S. Our live NASA TV launch coverage begins right here on March 1st at 4:30 p.m. If you'd like to keep up with updates on social media about GOES-S, please go to @NOAA Satellites. Thank you, and thanks for joining.